In problem 24.11, we have a cylindrical capacitor, which is kind of a weird thing. It's basically, it's going to have two, let me see if I can draw this. Okay. It's going to have two of these. Let's try that again. It's going to have two circular pieces. One of those in the center. Okay. And then there's going to be a charge on the outside and a charge on the inside. There's no reason to choose one as positive and one as negative. It can be either way. And they want to know, to start with, they're going to tell you that the inner radius is 3.5 millimeters, or the inner radius is 1.5. So this inner radius is 1.5, and this outer radius is 3.5. Okay, and they tell you the whole thing is 2.8 meters long. Okay, and then we know the capacitance per unit length. So to do that, we're going to start with just definition of capacitance. Capacitance is just the charge divided by the voltage between the two plates. In this case, they're just rolled up plates. Okay. But the tricky part of this is that we're going to have to actually derive this thing, which is going to be negative E dr. This is going to be from the outer plate to the inner. And we're going to actually have to derive what that electric field is. And again, we want the electric field on the inside. So we want the electric field here. That's going to be the Gaussian cylinder that we're looking at. That's the part we're interested in. So to do that, we're going to have to say, because this is going to be our Gaussian cylinder, we'll draw that out. So we're going to have to use Gauss's law to do that. So E dot dA equals Planck over epsilon naught. Okay. And so we have to do that part first before we can do anything else. So again, we've got a Gaussian cylinder inside there. Okay. So we're going to have E times the area of that cylinder, the surface area. Remember, it's not going to include the caps. So it's going to be 2 pi r L equals, again, we're going to call whatever charge it is capital Q over epsilon naught. And that's going to make E equal to Q over 2 pi r L. Okay. And you kind of expect that, that as you go further away from that plate, it's going to get bigger and bigger. Okay. And that's all I've got on the inside. So now we have to derive this expression over here. What's going to be the electric potential? Okay. And then we can find out, remember, we're solving for not capacitance, but capacitance per unit length. So that's going to involve a little bit of gymnastics too. So we're taking the electric potential between the outer and the inner, which in this case is going to be 3.5 millimeters, 0.00035, and 0.00015. Those are in meters. And it's going to be this whole expression, Q over 2 pi r epsilon naught dr. You can see right away, there's only one variable really here that's not a constant. It's going to be that. So let's take all these things out. Negative Q, that's a constant. And 2 pi is obviously a constant. And so is epsilon naught. And then we've got those 2.00035 and 0.00015. 0. I think I have one too many zeros. 0.15. That's 1 over r dr. We know that's a natural log is what the integral of that's going to end up being. So it's going to be negative q over 2 pi epsilon naught. We'll put the negative in front. And it's going to be the natural log of 0.0015 minus the natural log of 0.0035. Okay, so, and again, we're just going to subtract those. And when we do that, we get, I think it's, you get negative 6.5 for the natural log of 0.0015, and you get negative 5.65 for 0.0035. When you combine it all together, you end up with this expression. You get 0.85q over 2 pi epsilon naught L. Yeah, there's an L over here, and we didn't carry it over. There's an L. Yep. So, okay. So, yep, we got that too. And there's epsilon naught there too. We didn't put in either. Okay. So, all right. Now, our last step is to come up with this capacitance per unit length. So I'm going to actually take this whole thing and sub it over. So I've got C equals Q over this whole monstrosity, 0.85 Q over 2 pi epsilon naught L. I think that's all of it. Yep, that should be it. Okay. Well, those divide out pretty nicely. And if I take this, I have C equals 2 pi epsilon naught L over 0.85. Ooh, I can bring the L over here. Divide both sides by L, and I get 2 pi epsilon naught over 0.85. That ends up being 6.54 times 10 to the negative 11th. Okay. And that's farads per meter. Okay. Looks a little messy, I know, but if you notice, we did 3 different things. We'd come with what that electric field was first. Then we'd come with this messy expression down here for what the capacity, what the voltage was. Then we had to sub that in here and eventually end up with this thing over there. And that gave us our capacitance per unit length. The next part of the problem, part B, is actually a lot easier. They just want us to find the charge. They give us the voltage and they want us to find the charge. So we know that Q equals CV. And we actually know C over L. So we can find it's going to be C over L times the length of the capacitor times the voltage across them. I should have written that like that. Okay. So, and we actually found this in the other part. So it's going to be, what is it? It's 6.54 times 10 to the negative 11th. And that is the number of farads per meter. They tell us the length of the capacitor right here, 2.8 meters. And they tell us the voltage, 350 millivolts, which I'm going to convert to those divide out. Okay, farads times volts is going to give me coulombs. When I multiply all that stuff together, I get 6.4 times 10 to the negative 11 coulombs. Like I said, that was a lot easier than the first part.